Hi, Professor Jeff Sexton. I'm going to go through the assignment number 62, the PSLM Chapter 6, Random Variables. Alright, let's get ourselves started here. Trying to focus in just a little bit for you. So first we are asked to go through here and see exactly what's going on with this PDF curve here. Measured in here with also the cumulative distribution function, and we're asked to correlate these two and shade in the region underneath the PDF curve whose area is measured by the y slot and the plotted point here. So again, these are going to be lining up and working together here. So this is the probability density function. This is the shaded region that we are looking for as I move over and shade that region for you. Sorry about that. Then we're asked to use the plot to estimate the probability density function of this graph here, so from 0 all the way to 5 on this, and that would be the whole allotment basically. So I assumed it would be closely equal to 1, or the full value, all points, all data on that probability density function. Moving forward, we're looking at a cumulative distribution function in tandem again with another PDF curve. And we're asked again to shade it similar to what we just did there. So again, I went ahead and shaded out this region that would correspond to the point. Then we also wanted to estimate here from -1 this time all the way back to 8. And then I did a little math on the side. This came out to about 43% of the data underneath the curve here of the PDF function, which means that about 57% is going to be right over here. Of that graph. This is the most, the bulk here is going to be here in this PDF function, the lesser amounts over here of the data set represented by that PDF curve. In what sense is data set also a random variable? We know that the bigger the data set, the more random in form that data set will be. So if you always have a large enough data set, that you can always go ahead and extrapolate from that more of a random set of information, where a small set of data is not going to give you a true randomness, not big enough, not enough data, and it's going to be more predictable and more out there. Can a data set be continuous random variable? Yes, a data set can be. You may assume that any numerical value in an interval or a collection of intervals can be a continuous random variable. Try to zoom in here a little bit for you. The cumulative distribution function of a random variable x. How do you get the probability density function? So we're going to be taking the derivative of that to find of the CDF to get the probability density function. We're talking a lot about derivatives in this chapter. Is the cumulative distribution function of a discrete random variable plays the role of a probability density function. So we're going to describe the likelihood of the discrete variable to have a given value. That would be what we're doing there. From here, we're going to go ahead and see which plot is going to be a continuous random variable. So up top here we have a discrete, so you can see this is going to be named points as we keep going up, 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 up until we hit our 1 point in this CDF. Down here is going to be our continuous, so it's a nice even curve. It's going to be every point there showing from 0 to 1, from no points to all points, whereas here we have a data set, so it's kind of herky-jerky, goes up and down, blah, blah, blah. We then are asked to find, and this kind of goes to the next point, the mode. So can't really see it here, but this keeps on going. Our mode would be 5. It's our most frequently occurring number in the data set in the graph that was given. From here, we need to plot the PDF of a continuous random variable. So here is the plot, rather. We wanted to see what the mode would be. The mode is going to be the pinnacle of the graph here, so I estimated that to be about 3. So that pinnacle of that PDF is going to be the mode, the most frequently occurring piece of that graph. So now we have a corresponding CDF function here. And then we always wanted to say, what is the correlation between these two graphs? We can always see that the CDF function is going to be increasing the most rapidly where the bulk of those points are, which is going to be right around to the left and to the right of that expected x value of that pinnacle of the PDF graph. So this is exactly where the CDF function starts rocketing upwards, and then it will balance out and even out as the data progresses, and also back here, if we wanted to extend this back, this would be evened out as well. So evening out as the PDF frequency of data is going down, the CDF function is going to be leveling out as well. Leveling is a good word. Explain the statements of discrete random variable. A probability of x can be less than a may not be equal to the probability of x less than or equal to a. This is true. We're going to be dealing with a set number, a set of numbers. This is going to be discrete. It's going to be a set. So it's not continuous. So it could definitely be that could be the case. On a continuous random variable, however, it also could be true. We're dealing with any numbers on an interval. So you give us the interval, it's going to be every single number, a continuous function all the way through from that set interval a to b. So again, that could be true as well. I would say it would be true. From here, on the cumulative distribution function, so we're asked on this graph here to add in our cumulative distribution function for a discrete random variable approximately. So again, we're going to be looking at a discrete, so we're going to be having points. So now we're going to be going up quickly here, so big boxes up staircase wise, and then those staircases get a lot smaller as you continue on, and this graph kind of even levels out again. Alright, some hand calculations here for some of these expected values. So we're going to be going through here on an exponential function. So then we wanted to go ahead and show what the expected value of x would be. So we're going ahead from 0 to infinity. We're going to do f of the PDF of x would be the function to go ahead and give you the value of what you're looking for there. Similarly, we had a beta distribution here. So again, we're going to be looking at this beta distribution from the points given and also from the equation given here. Take the derivative of said function here. We'll first take this x squared and distribute it out, take the 12 and distribute it over as well, and then go ahead and take that derivative, antiderivative rather, of these functions here. So we're going to come up with a 4 to the 4x cubed to 3x to the fourth, and we go ahead and evaluate that integral from 1 to 0, and we come up with an expected value of 1. Going forward here, looking from a to b, and we're going to be calculating expected value and variance. So we know our expected value, as I move this over here, is going to be from a to b of x of PDF of x dx. And then the variance, I wrote it twice, I kind of squished it in. Variance is going to be the integral from a to b of x minus a plus b over 2 squared PDF of x dx. And then we were asked over here on the PDF of a random variable taking values between 0 and 2. This can be done. So if it's a continuous random variable, again, with PDF of x, we do have an integral f of x dx equal to 1, so we can integrate that f of x and find what we're looking for in the random variable section. Then we are asked to go ahead and create what this would look like from 0 to 2. So from 0 to 2 f of x dx, again, we find that derivative from there, and then we evaluate that integral 2 to 0 and get z equals to 2. So furthermore, we're going to be asked from 0 to b, so what happens when you keep b as a random variable, f of x dx. So from there you take that derivative, so now we have 0 to b of x squared, and find that bx squared would be that integral. Examples, real life, what does this stuff actually do for us? So from here, we wanted to see what's a normally distributed random variable going to give us. You can do velocities of particles in a system of a thermodynamic equilibrium would be a good example of a normally distributed random variable function. An exponentially distributed random variable would be more like a particle decay half-life of radioactive particles. We've done that one before in examples. From a Weibull distribution, it's going to be more of extreme events such as one-day rainfalls, data collection of out there statistics. And then from a Pareto distribution, we're going to be looking at the size of human settlements of a few cities and many towns, or similarly the values of oil reserves and oil fields from many small, very large fields, or few large fields and many small fields out there. So similar distribution. Now we're going through here, loss of a medical insurance policy. So what we want to do here, we're given this function. We want to find the derivative of that. We find the second derivative of that function there. Set that one equal to 0. Go ahead and manipulate this so that we can go ahead and say that x would be equal to 2. So that would be the expected value of loss amount. I think it was in millions as well. From here, we are asked again to find the expected payment of a warranty. From here, we went ahead and used this original graph here to give the integral here from 0 to 7 as we were given. We also knew that the mean would be equal to 10, so we throw the mean equation in there as well. So now we have this first equation plus the mean of dx. So we went ahead and pulled out the like terms here. So we pulled out this 10th, we pulled out this e to the 7th. We went ahead and just left us with e to the negative 0.2 plus the e to the negative 0.1. So we had e to the negative 0.3t dt, evaluate that integral. So now we have e to the negative 3.t minus 1 over negative 0.3 times the 0.1 e to the 7th. And we go ahead and have our 320 value there for that expected payment from a warranty. Again, it's all about taking those derivatives. Finally, we had the insurance policy question. So again, we're given